Good afternoon. Today's topic is Instruction Level Parallelism, ILP. So we know the main characteristic of computer is speed. So the speed can be increased in several ways. First, by increasing the clock speed, we can increase the speed of computer, or by reducing the number of clock per instruction, we can increase the speed. And the third way is by parallel processing, we can highly increase the speed of computer. Today's lecture focus on the third technique, that is by parallel processing we are going to increase the speed of computation. Outline of this presentation: start with the basic, that is what are instruction, what are the steps involved in the execution of instruction, then the comparison between sequential and parallel execution, and what is ILP, what are the challenges in ILP, so what way the challenges are resolved using the techniques. So that are all discussed in this session. Instruction execution, a language processing system. C equal to A plus B, a high level language statement that is converted to instruction by the compiler. The processor only work with the registers, so look out the instruction, the variable A is moved to a register R1 and the variable B moved to the register R2. Then the processor do the addition operation between the two registers R1 and R2. Finally, the result is stored back to the variable C. Anyway, this is our high level language statement that is converted to a mnemonic instruction by the compiler. Then naturally the instructions are in lengthy one. So in order to reduce the length of the instruction, the instructions are encoded into a 2-digit code that is called operation code. We call it as opcode. Then the opcodes are stored in the memory. Then at the time of execution, we are going to read the instruction from memory and start our execution process. Various stages in the execution process. We start with IF, instruction fetch, or read the instruction from memory, that is step 1. Then we know the instructions are in encoded format, that should be decoded, so that we have a stage, instruction decode. So here the processor going to regain the actual form of the instruction, decode. And also in the second stage, the register operand are going to be read. Now the processor know what is the instruction, what are the operand, so that it may go for execution. So after this execution, if there is any memory reference instruction, then it go and do this stage, memory operation. Otherwise the results are right back to the appropriate register in the stage 5. So these are the various stages in instruction execution, especially in RISC architecture, one of the computer architecture, RISC, reduced instruction set computer. So in RISC there are 5 stages, whereas advanced architecture, CISC, complex instruction set computer, there the number of stages may be more. An example for instruction execution, execution of arithmetic instruction. See, add R1 comma R2, arithmetic instruction. The actual operation is R1 equal to R1 plus R2. So here the source operands are R1 and R2, and The destination is again R1. Now the various stages. First it read the instruction from memory, then it is decoded, instruction decode, and the required operands are R1 and R2 that are read out in this stage. Step 2, read R1 and R2. Now the processor know the type of instruction and the required operands R1 and R2 so that it may go for execution. So here the ALU, arithmetic and logic unit, going to do the addition operation, that is R1 plus R2, and the result is stored in a special register called accumulator, AC, right. Then finally in the write back stage, the content of accumulator is moved to the register R1, the write back stage. So these are the various stages of executing any arithmetic instruction in RISC architecture. Similarly, one more example, a memory reference instruction. It's nothing but a load or store instruction. Here a load instruction, load R1 comma R2 of 2000, right. We know we have several addressing modes. So one of the addressing mode, a displacement addressing, right. So here the operation is, it going to read the content of a memory location. The address for the memory location is the content of R2 plus 2000. So it going to load the data from the memory location and stored in the register R1. This is the operation. Now various stages. In step 1, going to read the instruction, that is instruction fetch. Then stage 2, decode the instruction. Then for calculating this address, we need the register R2, so that here the operand is R2, so it must be read here, step 2. Then in step 3, it going to calculate the effective address, whereas in arithmetic instruction, step 3 is used for arithmetic operation, whereas here the step 3 is used for address calculation. Anyway, now the address is available in the accumulator. Then because of a memory reference instruction, in step 4 it going to load the content of the memory location to MBR, another special purpose register, memory buffer register, and in the final stage the content of MBR is moved to R. So this way the arithmetic instruction may use several steps and memory reference instruction may use all the 5 steps in RISC architecture. Now a architectural view of the instruction execution, all the 5 stages: instruction fetch, decode, execution, memory and write back. So look out the diagram. A PC, another special purpose register, it's nothing but a program counter which maintain the address of the next instruction, that is given to the address unit. Using the address, it going to find the location of the instruction and do the fetch operation, that is stage 1, instruction fetch. Then the PC is automatically incremented, by the way it going to locate the address of the next instruction. Now come to the second stage, decode, it going to decode the instruction as well as it going to read the necessary register operand that are available here, register 5. Then the third stage, execution. So here we have the ALU, arithmetic and logic unit. The values are supplied from the register file, and already the processor know the operation, so it can do the operation. Then if it is a memory reference instruction, it going to work with the memory unit, and finally the write back operation. The final results are again write back to the register. So these are the 5 stages of a RISC pipeline. Now execution, instruction execution. There are 2 types of execution: sequential execution and parallel execution. A sequential execution, a clock cycle 1, instruction 1 is start the execution, fetch, decode, execute, memory and write back operation. So by the way, the instruction 1 complete the operation by clock cycle 5. Only after the completion of instruction 1, the instruction 2 may start the operation and complete by the clock cycle 10. Then the third one start with 11th clock cycle, then the fourth one start with 16th clock cycle. Anyway, in sequential process, first instruction is taken, complete the operation, then only it may go for the next instruction. That is sequential operation. Here there was no risk, simply take the instruction, execute the instruction and do the operation, but the required clock cycle is more. For example, for executing 4 instruction, it require 4 into 5, 20 clock cycle. So that is the only drawback with sequential operation, but there was no risk here. But we need to increase the speed. That is only possible with parallel execution, not with sequential execution. ILP, instruction level parallelism. So here we are going to apply our parallel processing concept. ILP is nothing but execution of more number of instruction simultaneously. That is ILP, instruction level parallelism, simultaneous execution of instruction. So for implementing ILP, it requires some resources, additional resources, because we are going to apply a parallel processing. It means it required several units, and also it required some scheduling algorithm, either by hardware or by software. It requires some scheduling algorithm. And the last one, naturally our program or our application should be matched to the parallel processing, then only we go for ILP. So these are the requirement for ILP. Now a pipelined execution or a parallel execution of instruction. So instruction 1 start at the clock cycle 1, then 2, 3, 4, 5. So in clock cycle 5, the instruction 1 may complete the operation, right? In clock cycle 2, listen, the first instruction, the operation fetch is completed in clock cycle 1, so that the fetch unit is free in clock cycle 2, so that the instruction 2 is use this fetch unit. So by the way, in clock cycle 2, instruction 1 do the decode operation at the time instruction 2 enter into the pipe and do the fetch operation. Similarly, in clock cycle 3, after the decode operation, instruction 1 may go to execution unit, so that a decode unit is free, that may be used by instruction 2, and the fetch unit also free, that can be used by a new instruction, that is instruction 3. Look at the clock cycle 5. The first instruction may come to the last stage, that is write back stage, and the second instruction may come to the memory operation, third instruction may be in execution unit, and fourth one in decode operation, and the fifth instruction may do the fetch operation. Anyway, here in clock cycle 5, there are 5 instructions are executed. That is ILP, instruction level parallelism, that is simultaneous execution of instruction. So in clock cycle 5, there are 5 instructions are executed simultaneously, right? Whereas in sequential process, for executing all the 5 instruction, as per our previous slide, it requires 5 into 5, 25 clock cycle. Whereas in instruction level parallelism, that is in ILP, it is possible to complete the execution of all the 5 instruction by clock cycle 9. So look how much of speed is enhanced in ILP. Okay, a speed up equation, execution time of unpipelined execution is nothing but a sequential execution, execution of a pipelined execution, it's nothing but ILP. Look at the speed, 25 by 9. So this much of speed can be enhanced using ILP, right? The speed up ratio is mainly depends on the number of pipe stages. So in RISC architecture, we have 5 stages, right? That is IF, ID, execution, memory and write back. we have 5 stages, so that we can yield this much of speed up. Whereas if you go for CISC architecture, complex instruction set computer architecture, the number of pipe stages is 10, so that a much more speed up can be obtained in CISC architecture. But while you go for ILP, instruction level parallelism, there are some challenges, otherwise called hazards. The hazards are grouped in 3 categories: structural hazard, data hazard, and control hazard. Hazard is nothing but some difficulties, incompatibility while applying ILP. So because of this hazard, the operation may be delayed. The delay is called stall. So that now the pipeline CPI, cycle per instruction, is the actual execution time plus the time for structural stall, time for data hazard stall, and time for control hazard stall. So the speed up equation may be rewritten as this: 1 by 1 plus pipeline stalls into number of pipe stages, right? So if the number of stall is increased, the overall speed up may be decreased. So here the challenge is how we are going to reduce the number of stalls. So the first one, structural hazard, otherwise called resource conflict. So look out the code. A first instruction, a memory reference instruction, load, right? Start the execution, fetch the instruction, decode the instruction, execute, then the memory operation. Similarly, all other instruction. Look out the fourth one, it start the fetch operation in clock cycle 4, right? So the first instruction, a memory reference instruction, it going to read a data from the memory. At the same time, the instruction 4 try to read the instruction from memory. So 1 and 4 both are try to access the same memory. One for read the data, other for read the instruction. So it is not possible to avail the resource for 2 instructions at a time. So this is called structural hazard. More than one instruction try to access the same resource. That is structural hazard. So no other way, we need to apply a stall. Stall is nothing but a delay operation. So now look at the diagram. The load operation, it do a memory operation in cycle 4. It is not possible to do this fetch here, so a stall is applied. So automatically the pipe is pushed one stage ahead. So in clock cycle 5 only it start the fetch operation, and the total completion time is now 9. Whereas without stall it may be completed in clock cycle 8, but with stall it may be completed in the clock cycle 9. That is the drawback, that is the challenge with structural hazard. Now the solution for structural hazard. So this is structural hazard, right? So we are applying the stall. So in order to use a single memory, here we go for 2 memories. One memory may support for instruction, the other memory may support for data. So by the way, by using 2 memory, it is possible to execute both instructions simultaneously. That is the concept here. So a separate memory called data cache that may provide the data for instruction 1. At the same time, another cache, another memory, instruction cache, that may provide the instruction for instruction 4. So by the way, the structural hazard can be solved. There is an example architecture here by Intel Itanium processor, right? Itanium processor. So look out this, a instruction cache. It's nothing but a memory, level 1 memory. So it may supply the instruction to the fetch unit. Similarly, here there is a data cache. It may provide the required data to the instruction. So by the way, the memory is splitted here, one for instruction, the other for data. By the way, the structural hazard can be solved. So not only for the memory, if suppose more than one instruction try to access the ALU, arithmetic and logic unit, so the solution is here, Nitanium processor. So look out this, a integer unit, 1, 2, 2 integer unit, 2 memory unit, and 3 branch unit, 2 floating point unit. It means it is possible to execute 9 instructions at a time. So by the way, by using multiple functional units or by using level of memory, it is possible to solve the structural hazard. Then the data hazard. There are 2 instructions, instruction 1 and instruction 2. A is the source operand, the destination is R1, that is the output of this instruction is R1. Take the second instruction, R1 is the input and R2 is the output. Output of instruction 1 is act as input for the second instruction. So this is called data dependency. Look at the definition. There is a dependence between the operands of successive instruction. Instruction 2 depends on the output of instruction 1. So that is data dependency. So no other way, the instruction 2 must be waited for the completion of instruction 1, right? So that is data hazard. There are 2 types of data hazards, true data dependency and name dependency. Example for true data dependency, look at the code, move R1 comma A, R2 comma B, and the add operation, add R1 comma R2, right? So this R1, instruction 3, the source operands are R1 and R2. So the R1 is the output of instruction 1. So output of instruction 1 act as input for instruction 3. So the instruction 3 try to read R1 in clock cycle 4, but the register 1, that is R1, is available only after the clock cycle 5. That is the problem, that is data hazard. Instruction 3 try to read R1 here, but R1 is only available after the clock cycle 5. So until the clock cycle 5, it is not possible to read R1 here. Similarly, R2, output of the second instruction, that's also referred by the third instruction. So that is only available after the clock cycle 6, but you try to access in clock cycle 4. It is not possible. Similarly, third and fourth instruction. The output of the third instruction is R1, that is act as input for the fourth instruction, that is available only after the clock cycle 7, but instruction 4 try to read it in clock cycle 5. So these things are not happened. So this is called data dependency, otherwise called true data dependency. Okay. Yes. So no other way, we need to delay the execution of the third instruction. Look at it. Add R1 comma R2, that is the third instruction try to read the source operand R1 and R2. R1 and R2 both are available only after the clock cycle 6. Only after the clock cycle 6, R1, R2 are available, so that the decode operation of instruction 3 only start at the clock cycle 7. No other way we spend all this stall here. So that is the drawback, that is the challenge in true data dependency. Now the solution for true data dependency. There are two solutions. One is operand forwarding. The another one is scheduling. Right? So in operand forwarding, yes, operand forwarding, the normal execution. So only after the write back stage we can read the register. That is the problem. Instead, the operands are ready at the end of execution state. Instead of waiting for the write back stage, we are going to take the result of the previous instruction from here. See, instead of take the data after the write back stage, we are going to take the output of the previous instruction from the ALU directly. By the way, we can reduce the stall. See, so without operand forwarding we need to spend 3 stalls, but with operand forwarding, so what is operand forwarding? If the execution is completed, we can take the result from ALE directly, right? So by the way we can reduce 2 stalls. So that is operand forwarding, right? Then the another solution for true data dependency is scheduling, right? Take this example. There are so many instructions, right? The operation is actually C equal to A plus B and F equal to D minus E. That is the operation, the instruction. So look out the dependencies. R1 used by third instruction, R2 used by third instruction, there is a dependency. Similarly, this R1 is used by the fourth instruction, so there is a dependency. So executing all these instructions as per the programmer order is called in order execution. Executing of instruction as per the programmer order is called in order execution. So if you execute the instruction in order, we need to face all these dependencies. There are so many dependencies, so that we go for scheduling. It's nothing but change the order of execution. See, there is one order prescribed by the programmer. Now the compiler or hardware going to change the order of execution without violating the result of the program. Okay, so look out it. Take the first instruction as such, second instruction as such, right? But the third instruction a dependent instruction, so that in order to execute the add instruction as third, we may change the order. Take this instruction R3 comma D. So here there was no dependency. Similarly, move this instruction. Now the add instruction going to be executed here, right? Actually, the add instruction must be executed as a third instruction. Instead, we are going to execute it by a fifth instruction. So during this time, the necessary operands are come to this unit, so that we need not to apply any stop, right? Similarly, the sub instruction, the dependent values are from third and fourth, so we have enough time here so that it may read the data in time. Then the result of R1 may be moved here, the result of R3 may be moved here. So anyway, by a scheduling, it's nothing but reorder the execution, we can highly reduce the stalls in true data dependency. Next one, name dependency. Name dependency, right? There are 3 instructions, I, J, K, right? So here there was no true data dependency. We know what is true data dependency is output of the first instruction act as input for the second instruction. That is true data dependency. Whereas here, yes, R1, R1. The R1 is used by instruction 1 and 2, right? But this R1 is not the output of this instruction. So there was no true data dependency. But the instruction J tried to write something to R1. this is happened only after the read of R1 by instruction I. See, we know what is scheduling, we can change the order of execution, but here it is not possible to change the order. So first the instruction I read register 1, then only instruction J may go for write operation, otherwise it violates the result. So this hazard is called name dependency, and the type is called anti dependency, otherwise called var hazard, WAR, write after read. See, J can write the content to R1 only after I read the content. So that's why it's called var. Write only after the read, var hazard. Right. Similarly, J and K. So J try to write the content to R1. Similarly, K also write the content to R1. Both try to write the content to R1. But as per program order, the first write should be done by J, then only K can write the content. So this hazard is called wow hazard. Write after write. So K can write only after the write of J. This is called output dependency. Okay. Anyway, these two comes under name dependency. The solution for name dependency is renaming. See, take this output dependency. The problem is both are try to write the content to R1. That is the problem, right? So this can be solved by renaming the register. Instead of using R1, we may go for a new name for this output, that is yes, register renaming. So the name dependency can be solved using the technique called register renaming. Third hazard, control hazard. The most important compared with the previous two. So we have three hazards: structural hazard, data hazard, and control hazard. Compared with structural and data, the control hazards are more that is taking more stalls. So we need to avoid the control hazard in the execution. So take this code, a jump instruction, jump 0 R1 comma 2012. It means it going to check the value of R1. If the value of R1 is 0, it may jump to this location, that is it go and execute the instruction 4. If this condition is true, it going to execute the instruction 4. If the condition is fail, it may execute the instruction 2. Okay. So based on the condition, whether it is true, it may take this. If it is false, it may go for this. But as per our pipeline process, see, look out this pipeline. Instruction 1 enter into the pipe, that is fetch, decode. At the time of decode operation, the second instruction enter into the pipe. That is the nature of ILP. First instruction, second, third, fourth consecutively enter into the pipe. But if the branch condition is true, we need to execute the instruction 4. The condition is failed, we can execute the second instruction. But the decision is made only after the completion of this instruction. Okay. So we need to check whether branch condition is true or false. If it is true, we need to execute something, otherwise we need to execute the other thing. So it is not possible to decide the next instruction in the clock cycle 2. So no other way, we need to clear this stage, right? No other way, we need to apply the stalls. See, look out this, compare with the previous two, structural hazard and data hazard, it require more stalls. So only after the clock cycle 5, it may decide whether the branch is taken or not. So based on the branch condition, either it allow the second instruction or the fourth instruction. So that is control hazard. Okay. Right. Now the solution. The solutions for control hazard. Right. One of the solution for control hazard is branch prediction. Prediction. It means, see, in this we can find whether the branch is taken or not in the clock cycle 5. So until it is not possible to start any instruction. Okay. So we are going to apply some technique. By the way, we try to find whether the branch going to be taken or not in the earlier stage. See, such execution, it is found at the clock cycle 4. Only after the fourth clock cycle we can find. Instead, using some technique, we are going to find whether the branch is going to be taken or not in the earlier stage. By the way, it is possible to start the next instruction earlier, we can reduce some stop. So that is the concept in the branch prediction. Prediction. It may be wrong. Sometimes the prediction may be wrong. Okay. There are two types of branch prediction: static branch prediction and dynamic branch prediction. So static branch prediction is done by the compiler at compilation time. Why it is called static prediction is, once it is predict, that is followed by the compiler. Whereas in dynamic branch prediction, it is done at the runtime. So based on the runtime situation, the prediction may be varied. That's why it's called dynamic branch prediction. There are so many types. The first one in static branch prediction, the first one is always not taken. So based on some assumption, the compiler go for the prediction based on some assumption. So here the assumption is branch is always taken. So the compiler assumes that the branch going to be taken. It means the condition is true, so that it going to execute the target address, not the next address. So that is branch always not taken. So the branch is not taken, right? So look out the example, a branch instruction. If the branch is not taken means it going to execute the second one. If the branch is taken means it going to execute the fourth one. Okay. So by the way, branch is always not taken. A branch instruction, it does not going to taken, so that it going to execute the next instruction, instruction 2, 3, 4, 5, like that. So this is simply a static idea. This may be wrong. This may be wrong. If it is wrong, no other way. We need to clear all these things and allow a new instruction. No other way. Okay. So the prediction rate is only 50% in this technique. Branch always not taken. Similarly, branch always taken. So the compiler assumes that the branch going to be taken. So it going to execute the branch instruction. And what is the next one? The branch target. Because the branch is assumed as taken, so it go and execute the fourth instruction here, then fifth, sixth, so on. So this also a 50% accurate prediction mechanism. Then another one technique. Suppose in branch statement there are two branches, forward go to and backward go to. If the branch is going to a forward direction, that is forward go to. If it is go back, the program sequence, that is called backward go to. So here the assumption is backward going branches are always taken, right? Forward branches are always not taken. So here two assumptions are going to be applied. If it is a backward go to, the assumption is taken. So based on that, it is going to allow the instruction, right? If it is a forward go to, the assumption is not taken. based on that it may allow the next instruction. So here also the accuracy may be less, but comparatively better than the previous two cases. Then the fourth one is profile based. Profile is the compiler going to assess the previous execution of the code, whether the previous executions are taken, branch is taken. Now it come to the solution, come to the conclusion, so the branch is taken. If suppose the previous cases are not taken, or the fourth iteration is taken, the fifth iteration is not taken, so based on the previous profile the compiler going to take the decision, profile based. And the last one is delayed branch technique. Delayed branch technique, right? So here any branch instruction, so here the challenge is what is the next instruction we are going to allow. That is the challenge here. What is the next instruction we are going to allow? So in delayed branch technique, right, the compiler going to identify some independent instruction. Okay, independent instruction. It means the instruction is totally independent to the branch operation. Whether the branch is taken or not, it's not a matter, that instruction must be executed. That is independent instruction. So such type of instructions are identified. That instructions are allowed as second instruction after the branch instruction, right? The compiler going to identify some independent instruction that are allowed as second instruction. So the third case we can find the actual case, a delayed branch. Okay, see, look out this, whether a taken branch, the branch instruction, the second instruction is a delayed instruction allowed, then for taken it may go for the target, then the next. Similarly here, even though the branch is untaken, the second instruction is the independent instruction, branch delay instruction. Then during this time the compiler may identify whether the branch is taken or not, then it may go for the decision. So these are the various static branch prediction schemes. The summary. So on the whole, the main characteristic of the computer is speed. The speed can be increased by several ways. So one of the way is parallel processing. Instruction level parallelism is one of the technique for increase the speed, but there are some challenges in ILP. So these that is structural hazard, data hazard and control hazard. The structural hazard can be resolved by using multiple bank of memory, multiple functional units, right? So by adding the number of resources, it is possible to avoid the structural hazard. Similarly, for data hazard, there are two techniques, that is operand forwarding and scheduling. So by operand forwarding, the stalls may be reduced, and using scheduling, it is possible to remove the stall. The third one is control hazard. Using some branch prediction scheme, the compiler or the hardware find the branch in the earlier stage. By the way, it can reduce the number of stalls. So these are the way for reduce the number of stalls. By the way, it is possible to increase the speed of computer.